What is going on, Algebros? It's Mr. C here, and in this video what we're going to do is use the rational zeros theorem to find all the real zeros of the polynomial function. First of all, remind ourselves of the problem that we want to translate this into. It boils down to solving this equation, f of x equals 0. So what I'm going to do is bring in the expression for f of x, set that to 0, 2x cubed minus 4x squared minus 34x plus 68 equals 0. And with any four-term polynomial, I recommend trying to factor it by hand using the factor by grouping technique. This may or may not work with factor by grouping, but I'm going to do the rational zeros theorem regardless. So in the case of a four-term polynomial that does not factor by hand, you want to defer to the rational zeros theorem. We'll first start by making a list of the potential rational zeros. Of course, that's going to involve a list for p, so divisors of the constant term, as well as a list for q, which will be the divisors of the leading coefficient. So let's start with the list for p. So we want to think about numbers that go into 68, including the negatives. Plus or minus 1 does. Plus or minus 2. 3 does not go into it, but 4 goes into 68. So plus or minus 4. The next number that would go into it is plus or minus 17. Then plus or minus 34, then of course plus or minus 68. Now the list for q, so the divisors of 2, including the negatives, will be plus or minus 1, plus or minus 2. And then this is going to help us form the list of potential rational zeros by taking all of the factors of p as numerators and all the factors of q as denominators. So our first potential rational zero is plus or minus 1 over 1, or simply plus or minus 1, then 1 over 2, then plus or minus 2 over 1, plus or minus 2 over 2. We can X that off because we already have that in our list as 1 over 1, plus or minus 4 over 1, plus or minus 4 over 2, which you can cross that out, plus or minus 17 over 1, plus or minus 17 over 2, plus or minus 34 over 1, plus or minus 34 over 2. You can cross that out. That's the same as 17 over 1, plus or minus. Then plus or minus 68 over 1. Then plus or minus 68 over 2, which we already have 68 over 2 in the list. So if there are any zeros that are rational numbers or integers, they're only going to come from this list. Now if you keep track of all the unique fractions, we're looking at 2, 4, 6, 8, 10, 12, 14, 16 different fractions in here. Now the most number of zeros that this polynomial is going to have is 3, and actually according to the fundamental theorem of algebra, this polynomial function is going to have exactly 3 zeros. So where do we go from here? Well, my recommendation is to get a graph of the function going. So in just a second I'm going to pull up my graphing calculator, and in y1 I'm going to enter in the expression of the polynomial, 2x cubed minus 4x squared, so on and so forth. Alright, so that's 2x cubed minus 4x squared minus 34x plus 68. Then I'm going to hit zoom and select option 6. Alright, so I'm going to go ahead and sketch that out in my coordinate plane. So it went a little something like this. That's the graph of y1. So clearly we're not seeing any maximums or minimums, but that's okay. With regard to finding the zeros of a polynomial function, we want to keep track of the x-intercepts. And based on what the graphing calculator is displaying, we can see that there are 3 x-intercepts. And we want to just kind of eyeball where we think one of the intercepts is at. So if it were me, one intercept that's kind of on my mind is the intercept of -4, or the potential intercept of -4. So I'm going to actually show you a neat little trick that you can do to either confirm or dispel your guess. So I'm going to hit trace, and I'm going to type in -4 and press enter, and nope, -4 is not a real zero. That's because the y coordinate at -4 is 12, and it should be 0. So we try a different one. So maybe x equals 2. So I'm going to hit trace, press 2, and hit enter. And bingo, that's one of the real zeros. And it happens to be a real zero that comes from our list of p over q. So going back to the solution here, we know that x equals 2 is a real zero by virtue of our graphing calculator. And what we're going to do in addition to this is use this real zero of 2 to begin factoring the polynomial function. Now, in order to do that, what you're going to have to do is perform some synthetic division. What I'm going to do is put 2 in a little half box like that, and to the right of this 2, I'm going to list the coefficients of the polynomial function. So 2, -4, -34, and then 68. And there's the rest of my setup. The first thing we're going to do is carry down this 2. And then I'm going to multiply the 2 that's in the half box in the upper left-hand corner by what I just carried down. That gives us a 4. Now we add down. -4 plus 4 is 0. We use this 2 again to multiply the 0 to get 0. Adding down, we get -34. And then one more round of this multiplication by 2, we get -68. And in adding this down, we get a remainder of 0, which makes me so happy that I'm going to draw a dabbing emoji. So how does this help us to factor the polynomial function? Well, we know that 2 is a real zero, not only by our graphing calculator, but also now through the synthetic division. What you can do with this 2 is make a factor out of it, and the format of the factor always goes x minus the real zero. So for this reason, one factor of the polynomial function is x minus 2. Once that's factored out, there's going to be a remaining factor built by using these values from the synthetic division. So by the way, the second factor is going to be quadratic because we started out with a degree 3 polynomial function, and once we take the factor of x minus 2 out, the degree drops by 1. So for this reason, this is why I'm writing 2x squared plus 0x minus 34, and that's still being set to 0. And of course, there's an easier way to write that second factor, 2x squared minus 34. As soon as you have broken down the polynomial to where one of your factors is a degree 2 polynomial, what I always recommend doing is just splitting up the factors and setting them equal to 0. So x minus 2 equals 0, 2x squared minus 34 equals 0. And we solve the equations independently. So this one, x equals 2, which we definitely knew that. For this one, you can actually use the square root property. If you wanted to, you can move the 34 over to get 2x squared equals 34. divide each side by 2 to get x squared equals 17, and then you have to take the plus or minus square root of 17. If the square root method doesn't apply, let's say maybe there's a term involving regular x, then I always recommend doing the quadratic formula. Sometimes factoring will work, but in other cases factoring won't. So I think it's just easier to do quadratic formula regardless, unless you see the opportunity to use a square root method like I did here. So here are our zeros. There are 3 of them. We have 2, positive square root of 17, and negative square root of 17. Alright, so for that first part, we'd select option capital A. We'd type in 2, comma, square root of 17, comma, negative square root of 17. It does want us to factor the polynomial function, so here's how I do that. I create what's called a zero factor table. So it's going to be a T-chart, and in the first column are going to go the zeros, and then the second column will be the factors that we build. And keep in mind the format of the factors is always x minus the real 0. So as we just saw a moment ago, our zeros were 2, square root of 17, and negative square root of 17. Applying the format x minus r, our first factor is x minus 2, which that showed up in part of our work above. A second factor will be x minus the square root of 17. And then the third factor will be x plus the square root of 17. And the reason why it's plus is because of a double negative. So here comes the factored form of the function. I'm going to write all 3 of these factors next to each other. And last but not least, I left a little bit of a gap between the equal sign and my first factor, x minus 2. And the reason for that is because the leading coefficient of the original version of the polynomial function is a 2. If we were to leave our polynomial function as is right here and FOIL out all 3 factors, the leading coefficient would be a 1. So to quickly fix that, all we have to do is fill in that little gap with a 2. Alright, if the leading coefficient of the polynomial function is already a 1, then you really don't need to worry about this. You only need to worry about the leading coefficient being inserted in your factored form if the leading coefficient is different from 1 right out of the gate. So, to wrap this problem up, f of x is equal to 2 times x minus 2 times x minus the square root of 17 times x plus the square root of 17. And that's where the pain and torture, fun and excitement for this one ends as well. Alright, let me know if you have any questions. Otherwise, I hope you felt the fun in functions for this one. See you next time.